something more fun to speak about is programming languages and how you become, efficient in building systems where you can do data science in different ways. And I know you have some passion and affiliations
A couple favorites, yeah.
We have a couple of favorites at the table. Which one is your favorite? You live in Python, we know that.
No, I mean...
You don't?
Yes, but it's not by choice, but it's by necessity.
Basically. For the company.
I'm certainly not fond of the syntax and whatnot. But anyway, it's basically the go-to and certainly the number one language in the world today, even more than Java or whatnot.
Yeah.
And why do you think that is, if you were to speak about Python to start with, and why it's the data science go-to language right now?
Because it's easy for noobs to program with. Yeah.
Why is it simple? Just because all the libraries?
Because it's duck-typed. It doesn't have... It just has a very simple syntax, all that kind of thing. You don't have to worry about very much.
And the main problems with Python is what you would say?
The main problems with Python, if we speak in very general terms, is that the syntax is so permissive that it doesn't allow the language to make any smart decisions for you. So it has to figure out everything right at the last second, which means it becomes very slow. Another thing is that the syntax is not is simple to learn, but doesn't necessarily lend itself well to expressing mathematical concepts. So if in some languages, you can write an equation almost the way it looks like on a math paper, whereas in Python, you're something dot obj dot function, and then you put it doesn't look very nice. So I'd say the two worst parts about Python are...
He's studying linguistics at university. So but he also expressed it. For him, Python, I do not get it. It's like learning a new language. I cannot get Russian into my head. I can't get Python into my head.
Yeah.
And he said, Julia, I get it. So he thinks Julia now is a lot simpler. For him, that made sense.
Yeah.
But maybe also because he's a mathematician, coming that way into it again.
It could be. I think Julia is super easy the syntax is super easy. My background is mainly C and a bit of assembly. And that was from operating systems. And the thing with operating systems is it's very seldom you write large pieces of code on your own. There's a very big, well-established code base that's very optimized already, and you go in and you maybe change something, or you rewrite a function or something like that. It's very seldom that you come with a new memory allocator that's 10,000 lines of code or something like that. And
so C, you using libraries.
Yes.
As well. Yeah.
And the thing I liked about C was that it mirrored how the machine works. Despite, I resented it when I came to university that everybody started off with Haskell. And the funny thing was that there were many kids from high school that knew how to program, including myself. And Haskell was so different that everybody was back at ground zero. So even the experts, they were like, oh my God, how do I express that as a Lambda function? I have no idea. How do you express Dijkstra's algorithm as a function? Who knows? But the teachers were like, this is the epitome of beauty. You think in parallel. Why shouldn't we program in parallel? And
theorists.
I couldn't. I don't know. I think I'm
waste of time.
I'm a bit contrarian, so that's why I was like, well, maybe it's not that way. And I refused to learn Java and all these other languages. And I remember at that time there was this one guy who was like, Python is good. It's duck type. If it looks like a floating point value, it is. And I'm like, is it float 32 or float 64 or a decimal or a big or a complex number? He's like, doesn't matter. It's good, bro. It works in Python. All right, sure. But then Julia came along for me, and it felt like it was still the machine, like C, but I didn't have to program that way if I didn't want to. So suddenly I could be 20 times more efficient without giving up that control that I felt like I had with C.
And for a lot of people that are at least somewhat knowledgeable about Python, how would you describe Julia to them?
So Julia has a number of pretty nice features. It has introspection. It has multiple dispatch. It's JITted. So you guys might be familiar with
just
compiled
in time,
just in time. Yeah, and you guys might know that from Numba or some PyPy or some stuff like that.
Java, perhaps.
Right? And the thing is, Java can be very fast if it's purely CPU bound and all that kind of stuff. But Julia is fast like that all the time. It's sort of awkward. You go to Wikipedia and you look up an algorithm and you program it basically the way the math formula works, and it's just fast out of the box. I don't underestimate speed, because like I said, if it's 10% faster, it's one thing, but this can be like 30, 300 times faster. That makes a big difference.
What is it that speaks against Julia? Because it's sort of there, but it hasn't taken off. And is it growing, or is it more?
It's definitely growing in niches. So like in gene sequencing, in economics, in very number heavy fields is where you see it growing the fastest. And now data science is a number heavy field.
So if it's better, why isn't it growing faster? Or
is,
like the Python nerds
Python is like 20 years old, and Julia is a couple years old.
Yeah, when did it come out?
It's maybe more than a couple years. It's like 6 or 7 years old, I think. But
exactly.
Yeah. No, but it's growing. I think it's like Dvorak. It's gonna be big one day. Yeah.
And another angle on languages, or maybe not languages, but using GPUs for visualization.
Yeah.
I think you've been playing around a little bit with Omniscient and stuff like that.
I think you should take every advantage you can get. And for visualizations, sure. GPUs can be used for a lot of stuff. They're very hard to use on graphs, unfortunately. But there are a number of graph algorithms where you can solve them with matrices. And in those cases, it goes pretty fast, like if you want to solve it numerically. But I try to do as much as I can on GPUs, just because the things you can run on them run so much faster. And you can really do anything. We were talking with this one company that wanted to say, well, if you can do packet switching faster, then we're interested. I'm like, you can do that on a GPU. You just get one of those Mellanox cards. The packets go straight into the GPU, and dictionary lookups on GPUs, super fast. You can do it. Yeah.
So let's go here, because like from languages now, you like Julia and all that. How does that fit in now with the whole GPU programming? Or is it different? Or can you run Julia? Or
Okay, so one of the cool things about Julia that separates it from Python is precisely that they've been really thinking about making the language introspective in such a way that it can make really smart decisions about everything. It's very composable. And this is going to tie into something that maybe you want to talk about in a sec about auto differentiation. But you can write Julia code that's pretty abstract, so that if it implements APIs that the communities has agreed on, like a matrix API, the underlying compute hardware is irrelevant. So
really?
You
can run it.
Yeah, so there are frameworks for machine learning, and one that I like is called Flux, and it uses just standard arrays, and you can run that XLA on the Google TPUs. You can run it on GPUs. AMD's MROC stuff is
quite flexible.
Yeah, you can run it on pretty much anything.
That's pretty cool. And one last angle on this. Let's see if I can get it right. No, let's leave it.
XLA and other techniques like LLVM and stuff that Julia has. How would you describe it? What does that do?
It's pretty sweet. Omniscient is a database that runs its filtering and aggregation, all that stuff on the GPU. So it's very fast. Either it works or it doesn't work, meaning if the data set fits in the GPU, it's just absurdly fast. And there's this really cool use case where you can have Julia code that you've written, and because Omniscient lives on the GPU and runs LLVM code, and Julia is JITted into LLVM, you can use a little macro called a little macro that converts your code into LLVM code, and then you can put it in as a user-defined function and run it on the GPU together with the database.
And what does that mean? What does that do?
That just means that
speed.
Yeah, more speed, more faster. Everything working together a little bit seamlessly. The big downside here is that with Python, you get these ready-made things that are really nice, and you don't get that with Julia, because AMD doesn't provide a TensorFlow version for Julia, and you don't get all that stuff for free. But if you're willing to invest a little bit in your own packages and that kind of thing, the composability is so powerful that you really, if somebody does an innovation in one package, you get all the benefits immediately. And the fact that most of the Julia ecosystem is written in Julia speaks for it quite well.
It's like Spark in some way, I guess, which uses Scala in some way.
Yeah,
and
yeah.
that it's actually using that in itself. And actually, this is I think, interesting analogy that would be fun to see what you think about. So you are a big fan of doing parallelization in different ways, and how to work with threads or processes or whatnot, or free BSD could be another topic of discussion if we go there sometime. But I started with big data many years ago, like 10 years ago or something, and the process of turning an algorithm from having it run in sequence in some way in a single CPU to actually run on parallel in many machines is surprisingly hard. And you have to rethink the whole algorithmic design. And a lot of people didn't understand that big, necessity to actually translate algorithms into a parallelized version. And I would say, and I would like to hear if you agree, that the same thing applies with GPUs. So GPUs have these thousands of cores, and instead of a CPU having tens or something, and you have to basically have a way to convert an algorithm to run on GPUs in a fast way.
Yeah.
And actually, it's a very similar kind of problem. Would you agree?
It's the exact same problem, and it's very tricky.
Yeah.
So I have this one fun story. We bought an NVIDIA, what are they called? The Jetson TX2. Now it's old. Now they have the newer, cooler ones. But it has a GPU that's about half, or maybe less, but let's just say it's about half the speed of a 1080, something like that. And we wanted to run real-time video object detection using YOLO on it. And so I implemented...
So YOLO is a deep learning network for doing object detection,
yes,
basically.
one pass, multiple object detection on an image. And the TX2 is really nice because it takes the video frames and puts them straight into the GPU. And so as long as you're in the GPU, you're in good shape. And we had some other challenges like memory allocation and stuff that was a little bit tricky with garbage collection. But one of the challenges was that there were these parts in the YOLO algorithm that required, so there's this one function in Julia called find first. You give it an array and it'll tell you where the first of a certain object is. So find the first number 5, for example. Implementing that on a GPU is not really easy. There's like a not elegant way of implementing that on the GPU. There are some references for how to do a scan like that, but there's no good way of parallelizing that. And so we were getting pretty good performance right up until that point. And so what we realized was we had to just take the rest of the stuff and run it on the CPU. And the first part was on the GPU. Right. And so some stuff, I don't know, we would probably have to rethink how YOLO works to get past that part. It's not easy.
But do you think it will come a point where Julia or other like Swift for TensorFlow or something, or Rust or Go, whatnot, kind of language will have sufficient intelligence, I guess could be one term to call these kind of compilers that are becoming increasingly intelligent in some way, to actually automatically parallelize algorithms that doesn't require you as a human to do that?
So no, I don't think so.
Okay.
I think they will get to a point where they will be able to tell if data structures are embarrassingly parallel and the operation you're trying to use on them. If like you're doing a typical operation, like I don't know, if you're doing a sort or whatever, and it knows that sort and this data set is parallelizable, it'll do it. It'll run it on threads or on the GPU. But there are some algorithms that just aren't parallelizable, that are sequential. For example, crack propagation in a rock. You can't calculate where the crack at one end is before you've started the crack.
It's a causality problem.
Right. And so some of that stuff you just can't get past.
So going on with the language part here. So moving away from languages, clearly when we talked with Carl to me and all that, we talked about putting data and AI in production. So what is your experience about the tooling landscape around let's say now Julia and all that. So how much are you living in the Kubernetes of things and all that?
Yeah, I think it's very unfortunate that it's gone so fast that it feels like a lot of people have just picked the first best thing they've found to get into production.
Deployment tools.
Yeah, exactly. Like Jupyter notebooks. Like Jupyter notebooks are fun, cool things to program together with your friends at the office because you can both be looking at the same notebook. And even that doesn't work very well. But it's a neat thing. You're not supposed to deploy a notebook like it's code. You can't even version control notebooks in a good way.
Well, you made Databricks very sad.
Right? Yeah, I mean, people have been working around this. It's like, that's the Python way. You just add more stuff to it and more money.
So tell me a little bit about your reference architecture, how you think around Julia, and when you want to deploy it, how you
Let me
think.
just give you an example about containers.
Yeah, let's do it.
Okay, so have you heard of singularity containers?
Nope.
It's the de facto standard for anybody that wants to run a multi-user system and containers. So if you go to any HPC installation, the Lawrence Livermore HPC, all these places, they run singularity containers. What job scheduler would you use when running those containers? Oh, Kubernetes. Kubernetes is not a good job scheduler. You have Mesos, but real people, they run Slurm, SunGrid Engine, that kind of stuff. Like, we have these really tough tools that are battle proven, that are good. And instead, we're using these sort of web developer toys, Flask and that kind of stuff, to put our stuff into production. And I think it's a missed opportunity.
Why is that? Is that because the AWS community grew up in web applications, and you need to get stuck with that enterprise tools?
No, but it works for them. It's not that it's bad tools.
No.
It's just that they've had version control and continuous integration, all these really good tools that work for web development. And then the data scientists, now they're like, okay, we have to actually have like structure to our development process. Let's do what they're doing. And they just take all the tools from that side. And
so do you think there's better tools out there that is not really being used?
Yeah. Same thing with storage and all that kind of thing. Like, just because Hadoop is good at storage, we got to use Hadoop now?
I think you open a bit of a Pandora's box here, but okay.
Let's go.
But speaking about deployment tools, there are a number of them that are becoming de facto standards.
Yeah.
Like
Kubernetes.
perhaps not only notebooks, but Kubernetes and these kind of other auto-scaling kind of tools. And then a lot of like scheduling tools and pipelining tools and whatnot. Yeah. But you mentioned some HPC tools, and I think this is an interesting discussion. And I've been recently also thinking or speaking about these kind of differences between HPC, traditional HPC.
What's this? What is
high performance computing?
High performance computing.
It's kind of big Cray computers or whatnot, doing whatever kind of weather simulations or biological kind of computation or whatnot. And then you have big data, which is the Hadoop or today's kind of Spark kind of tools or Dataflow or whatnot, or Flink and these kind of things. And then we have the whole like DPU, GPU kind of land, which is all different.
They're like three different ecosystems.
This is like three ecosystems: HPC, big data, GPUs,
machine learning, and sure.
Okay, keep going.
And then you can think, what is really the future in some way? Will they converge at some point? Are there clear differences in way of using them? So HPC will continue to move in some way with Slurm and whatnot? Or will basically everything converge even from big data into GPUs and this kind of... What's your thinking there? Will it converge or will it continue in the same kind of...
Well, what's very clear is the best product is not going to win. So, right? Because I used to think that FreeBSD was better than Linux in so many ways.
Yeah.
And, if you add 1,000 engineers to Linux, then Linux is better.
Yeah.
Supports more hardware, does all the things you want.
Similar place for Python, I guess.
Yeah,
similar for Python.
More people were using it.
Or TensorFlow.
Yeah, it's like, should I use Julia and rewrite everything? Or just use Python and use what everybody else uses and it works and I know it works.
Yeah.
And it's the same thing for these HPC tools. It's like Slurm is 1,000,000 times better than the scheduler that's in Kubernetes, but maybe nobody cares. Maybe it's not useful. I mean, I think it's useful. And it's the same thing with Singularity, where I can use Singularity on my laptop and it doesn't mess up my file permissions. And it works like I would expect it to with SC Linux, and it works with MPI, it works with GPUs. But maybe that doesn't matter because Windows ships with Docker, and it's just nice, So I don't know. But I don't think that really matters for big companies, because big companies have one sort of business, a core business that their revenue centers on. Or maybe a couple of core businesses, and they can afford to specialize. So
this is an interesting idea. What are you saying here? You're saying that if you have a bigger business with a core thing, pick what is right for you and don't pick the standard. Is that what you're saying?
I think so, yeah.
So
And I
basically,
think
if
that a
Slurm is
company-
the shit for Vattenfall in energy, go there.
I think so, but then you have to also be of the mindset that you can't sort of sleep on these things for 5 years.
No.
I mean, if that's what you want, if you want to buy a data warehouse and then live with it for 30 years, okay, then you shouldn't be buying Cloudera or something like that. You can go with Oracle, but...
Okay, and sorry, another
delicious.
continued discussion here. I mean, I think it's a really interesting discussion. What will happen with HPC in the future?
Yeah.
I know the EU Commission is going to invest huge amount of money in that, and you can question if that's the right thing to invest in, but still that's going to happen.
What's their bet that it's converging in that direction?